This is a video summarising all that you need to know about Group 7 for Paper 1 of AQA A-level Chemistry. The third inorganic chemistry topic covered in AQA A-level Chemistry Paper 1 is Group 7, also known as the halogens. These elements are found in Group 7 in the P block, and they all have 7 valence electrons in their outer shell. The name halogen means salt former because when Group 7 react with metals, they form ionic compounds known as salts. Most of the halogens are non-metals. Astatine is a metalloid or a semi-metal. Tennessine is a synthetic element that doesn't exist in nature, and it was only synthesized for the first time in 2010. It doesn't behave like the other halogens, so we'll say no more about it. As you go down the group, the boiling points of the halogens increase, so they exist in different states. Fluorine and chlorine are gases, while bromine is a liquid, one of only 2 in the periodic table, and iodine and astatine are solids. We can relate this to the size of their molecules and the van der Waals forces between them. The halogens exist as diatomic molecules consisting of 2 atoms covalently bonded together. As we go down group 7, these molecules become bigger and contain more electrons. So fluorine is obviously the smallest molecule, and at the other end we have astatine, which makes much larger molecules. Because these molecules are larger, they contain more electrons, and this means that the weak intermolecular forces that spontaneously arise due to the irregular distribution of these electrons are comparatively stronger and need more energy to overcome. It's this which leads iodine and astatine to have higher melting and boiling points and exist as solids. Just like group 2, as we go down the group, we're going to see that there is an increased atomic radius because we're adding a new shell each time. Electronegativity is the tendency or power of an atom to attract a pair of electrons in a covalent bond towards itself, and fluorine is the most electronegative element in the whole periodic table, with electronegativity then decreasing as we go down the group. This also means that as we go down the group, things become steadily less good oxidizing agents, so fluorine is a very good one, astatine is a much poorer one. The reason for all this is this larger atomic radius, including more shells. So this means that the outer shell electrons are experiencing more shielding, and therefore there's a decreased attraction between the nucleus and the bonding electrons. And this is really important. You need to be talking about the bonding electrons, not just outer shell electrons in general, because electronegativity is about attracting electrons that are in a covalent bond. This also means that the bond polarity decreases as you go down the group. So we know that when fluorine bonds, it makes very polar bonds often. And also this is going to mean that the bond strength also changes. In terms of the boiling points, we know that fluorine and chlorine are gases, where bromine is a liquid and iodine is a solid. And so all of these small covalent molecules are experiencing van der Waals forces. But because bromine and iodine are larger atoms and they make larger molecules that have more electrons, the van der Waals forces are stronger. This means that they take more energy to overcome, and therefore iodine is going to have a higher boiling point than bromine, and bromine higher than chlorine, and so on. The more reactive higher up halogens are able to displace the less reactive lower down halogens from their compounds. So for instance, chlorine in the form of chlorine water can displace bromine from potassium bromide. Chlorine water is a very, very pale green, almost colourless, and in this reaction we would see an orange solution forming as the bromine water formed. If we repeated this process with potassium iodide instead, we'd see a darker brown solution forming. You also need to be able to write ionic equations for this, in which case we would remove the spectator ions and just not include the potassium. And you also need to be able to write half equations too. I can show the differences in reactivity of the different halogens by carrying out a displacement reaction. So first of all, into my spotting tar, I'm going to put all of the compounds that these halogens are going to try to displace. So I start off with a water control, just so I can see what they all look like. And then I'm going to have some potassium chloride in my next set of wells. And then some potassium bromide. And then finally some potassium iodide. And you can see that all of those compounds are just kind of colourless liquids. So next I'm going to try to displace some of those halogens using some chlorine water. So this is literally just chlorine dissolved in water. And if I put those into that first row, we don't see a lot to start with, but when we get to this third well here that had potassium bromide in it, you can see a slight yellowy colour. And then when we get to the fourth well that had potassium iodide, a much darker colour. So next we've got our bromine water. So I put a little bit just in the water to start with, so you can see it's got a very, very pale yellowy tinge to start with. Not a lot happening with the potassium chloride or the potassium bromide.
But again, when we add it to the potassium iodide, we do see a difference. It doesn't look the same as our control, so that tells us that a reaction has happened and the bromine has managed to displace the iodine from the potassium iodide. And then finally, we've got some iodine solution, some iodine water. And this is where the water control is really necessary. So you can see it's already that dark orange colour. And so although each of these is going dark brown, it just looks the same as the control. So that is just the colour from the original iodine solution, and actually no displacement has taken place.
When sulfuric acid reacts with solid sodium halides, it can perform two different roles. Firstly, it acts as a proton donor or an acid. So if we have some sodium chloride reacting with sulfuric acid, we make steamy white fumes of hydrogen chloride and also some sodium hydrogen sulfate. And this process will happen for any of the halides, and they're all just functioning as bases. But then if we think about bromide ions and iodide ions, which are the best reducing agents, then the reaction is able to go a little bit further with the acid acting as an oxidizing agent. This won't work for fluoride ions or chloride ions because they're not powerful enough reducing agents. So if we take hydrogen bromide that was formed in the first reaction, this can be split up into hydrogen ions and bromide ions, and these can react further with the sulfuric acid to make some bromine and some sulfur dioxide and some water. And you can see here that the sulfur is moving from a +6 oxidation state to a +4 oxidation state, so it's being reduced and acting as an oxidizing agent. Now in this process we make this sulfur dioxide, which we can't see, but because the bromine is produced at the same time, this makes the fumes turn brown. And then if we think about the iodide ions, we have a slightly different process. So we have these 8 electrons here, they're coming from the iodide ions, 8 of them, being oxidized to produce 4 iodine molecules and also these 8 electrons. And this can happen because iodide ions are an even stronger reducing agent than the bromide ions. You can test for the presence of halide ions in solution by using acidified silver nitrate solution. We acidify using nitric acid to begin with because this will remove any carbonate ions from solution, and these would lead to a false positive because they would also give you a white precipitate. When you add the silver nitrate, silver fluoride would be produced if you had fluoride ions, but this is soluble so there isn't an observable change, whereas silver chloride will produce a white precipitate, and you should be able to write an ionic equation for this, showing how the two soluble ions form together to make this insoluble precipitate. So silver chloride is a white precipitate, silver bromide is cream, and silver iodide is yellow. And if we wanted to analyse those further, say look at how much was made, we could filter them out of the solution because they are insoluble. Now, if you produce just silver chloride or silver bromide in isolation and you don't have anything to compare them to, it might be hard to say whether it is white or cream. So we can identify this further by adding dilute ammonia, because silver chloride will redissolve in that dilute ammonia, but silver bromide will not. Small, carefully controlled amounts of chlorine are added to both drinking water and swimming pools in order to kill harmful microorganisms, despite the fact that chlorine is toxic. This is because, on balance, the health benefits about not having pathogens in that water outweigh the risks of adding a small amount of a toxic substance. Chlorine can react with water in 2 different ways, depending on whether sunlight is available or not. When there's no sunlight, we see the chlorine reacting with water to make 2 different acids, hydrochloric acid and chloric acid. This is described as a disproportionation reaction because the chlorine is both reduced and oxidized, going from an oxidation state of 0 in chlorine to -1 in hydrochloric acid and +1 in chloric acid. And we can describe these processes using half equations. In the presence of sunlight, we see a different reaction being undergone, and as well as hydrochloric acid, we also have the production of oxygen gas. When chlorine reacts with cold dilute aqueous sodium hydroxide, it produces 2 major products, sodium chloride and sodium chlorate. Going from the oxidation state of 0 in the elemental chlorine, in the sodium chloride, the oxidation state of chlorine is -1, and in chlorate, it's +1. So this is another example of a disproportionation reaction. This is sometimes referred to as sodium chlorate 1 to differentiate it from sodium chlorate 5, which we'll get to in just a second. So we have 2 major products here, and the sodium chlorate can be used for a variety of things, including making herbicides, explosives, dyes, cosmetics, pharmaceuticals, and paper. Then if the sodium hydroxide is hot, we have a different reaction going on, but this one is still a disproportionation reaction. So this time we have sodium chlorate 5, where the chlorine has an oxidation state of +5 instead.
And then the very last thing in paper 1 of AQA A-level Chemistry is the fourth required practical, which is a series of test tube reactions to identify cations and anions. Now we've gone through most of this already, but just to recap, we can identify which group 2 ion is present by looking at the solubility of their hydroxides and their sulfates. So if we add sulfuric acid, we're going to make a group 2 sulfate, and whereas barium sulfate is highly insoluble and forms a white precipitate, magnesium sulfate is very soluble, and so we would just see a colourless solution. If we think we might have ammonium ions, then we add sodium hydroxide and warm in a water bath so that ammonia gas would be given off. And then we test those fumes to see if they are ammonia gas with damp red litmus paper, which will turn blue in the presence of ammonia. As we've said, to identify group 7, we use acidified silver nitrate, which will form a white precipitate for chloride ions, a cream precipitate for bromide ions, and a yellow precipitate for iodide ions. And we can then also try to dissolve those precipitates using dilute ammonia, and the silver chloride precipitate will dissolve, but bromide wouldn't dissolve. If we think we might have hydroxide ions, of course, those are what are found in alkalis, so we can do some kind of pH test, usually red litmus paper, which would turn blue. To test for carbonates, we can add any dilute acid and we would see effervescence. And if we really wanted to be sure, we could test that effervescence with lime water, which would turn cloudy if it was carbon dioxide being given off. And finally, to test for sulfate ions, we use acidified barium chloride, which will form a white precipitate.
Thank you very much for watching, and I hope you're now feeling slightly more confident about this topic. If you have found this video useful, then don't forget to like and subscribe for more A-level chemistry videos coming soon.